Imagine pushing against a solid brick wall with all your might. You're generating this massive amount of force, right? But the wall doesn't move. Zero acceleration.
Yeah, zero. It just sits there.
Exactly. So does the physics just break? Or are there like hidden forces at play?
Welcome to today's deep dive. We're unpacking the source material on Newton's second law to see exactly how it links net force, mass, and acceleration.
It really is, the ultimate accounting system for the physical universe. I mean, it governs absolutely every movement.
And it all centers on one foundational formula, right?
Hmm.
Newton's second law basically states that acceleration is directly proportional to net force and inversely proportional to mass.
Right. And it's expressed as F equals m times a. In this equation, F means net force measured in newtons.
Okay, and the m means mass measured in kilograms, and a means acceleration measured in meters per second squared, right?
Exactly. So let's look at the real world implications of that. If you push a golf ball with a certain force, it just, vanishes over the horizon. Yeah, it goes flying. But if I apply that exact same force to like a heavy delivery truck, it barely nudges.
Right, because the truck's massive inertia just resists that change in motion.
Yeah.
So if mass stays the same, more force means more acceleration.
Got it. So if force stays the same, a larger mass means less acceleration.
The relationship is absolute. But let's go back to your brick wall example for a second, because it highlights a really major trap.
Oh, like why the wall didn't accelerate when I pushed it?
Precisely. Why didn't it?
Well, because my push isn't the only force in the room. I mean, I might be pushing forward, but the structural integrity of the wall is pushing back.
Exactly. And that is why the F in F equals m times A actually means net force, not just any single force.
Right, so you have to combine every single push and pull acting on an object first.
Yeah, you do. If your push perfectly matches the resistance of the wall, those forces cancel out.
The net force is zero.
Right. And no net force means no acceleration. But when those forces don't balance out,
Then the object always accelerates in the exact direction of the net force,
Yeah.
right?
you got it. It always follows the net force.
Okay, let's talk about how we actually measure that force, because hearing 1 Newton can feel a little bit abstract.
It can. But our sources define it really specifically. 1 Newton equals 1 kilogram meter per second squared.
Which basically means it's the exact force needed to accelerate a 1 kilogram object at 1 meter per second squared.
Exactly. We use this standard unit so we can translate all that chaos of movement into, universal data.
And when we chart that data on a graph, the physical reality becomes incredibly clear. Like if you look at force versus acceleration while keeping mass constant, you get this straight proportional upward line.
Because, well, more net force directly translates to more acceleration.
Right. But if you graph mass versus acceleration, keeping the force constant, you get an inversely proportional downward curve.
Yeah, because as mass scales up, its resistance to acceleration scales right along with it.
That makes total sense. And since this is a strict mathematical relationship, we can just rearrange the formula to find whatever missing variable we need.
We can. So if you want to know acceleration, A equals F divided by M.
And if you need the mass, m equals F divided by A. It's pretty straightforward once you see the pattern.
It is. Our sources actually outline a specific protocol for calculations, which really helps prevent you from getting lost in the weeds.
Right, like starting by just writing the formula down first.
Exactly. Write the formula, then substitute your known values, rearrange if you need to, calculate, and finally,
Check your units. I feel like that's where a lot of people trip up.
oh, absolutely. It might
Yeah.
sound procedural, but it's how you catch hidden variables. Like if you have a 4 kilogram object accelerating at 3 meters per second squared, you multiply those to get a net force of 12 newtons.
And if you don't track your units through that whole process, you kind of lose the physical reality of what you're even measuring.
Which leads us right into the common mistakes people make. Using a single force instead of calculating the net force first is a huge one.
Oh, yeah. And forgetting to rearrange the formula correctly, or like we said, leaving off those final units happens all the time.
But, the biggest conceptual trap really seems to be mixing up mass and weight.
Oh, right. Because mass is the actual amount of matter in an object, like its inertia.
Yes. And weight is just the local gravitational force pulling on that mass. I mean, your mass is the exact same on Earth as it is in deep space.
But your weight is completely different.
Exactly. If you conflate the two, your calculation for net force just completely falls apart.
So F equals m times a isn't just some abstract rule on a page. It literally dictates our physical world by perfectly balancing mass, force, and acceleration.
It really forces us to account for absolutely everything pushing and pulling around us.
That is wild to think about. Next time you struggle to push a heavy piece of furniture across the room, consider all the invisible forces involved.
Yeah, friction is fighting you, gravity is anchoring the mass.
And you're just trying to generate enough net force to break the stalemate. What hitting forces are combining to reduce your net force and resist your acceleration every single day? Keep wondering about that, and we'll catch you next time.